All right, so I trust that you have watched this video here, and it ends actually with a question about what's the upward force on you. But before we get there, so a force is and he outlines it in the video, you can call it in the simplest terms possible, it's a push or a pull. Okay, so if I've got an object here, I can think I'm going to either like push it some way, right? That's kind of what a push looks like. Or if I've got that same object and I'm kind of pulling it, if you attach a string to it or something, this is what a push looks like. And this is what a pull looks like. So let's take a look at the main types of forces in our course. So the first one that we were talking about that everyone got was this idea about force of gravity. And by the way, instead of force of gravity, you could just simply call it, I'll get this back, you could just call this weight. It is the exact same thing as just saying weight. So normally I don't write out the whole words force of gravity, I just say Fg, and we do have a formula that goes with this. It'll be coming up a little bit. Fg, that's the force of gravity, equals mass times small g. And I just want to outline what these things are. This whole thing, this not just the F, but the whole thing here, this is the force of gravity. And like all forces, is measured in newtons. This is mass, and that's measured in kilograms. And this one, I'll talk more later about it. For now, I can say this is the acceleration due to gravity close to the surface of the Earth. It's 9.8 meters per second squared downwards. Or sometimes we just average that out to 10 meters per second squared down. So you can put a negative out front to say down, or you can just write the word down. So just to differentiate, this small g is not the force of gravity. It's something that we sometimes refer to as acceleration due to gravity, or how strong the gravitational field is. So that's that first one. Let's go on to the second one here. The normal force. Now this is the hard one. When he was talking about, okay, here's Derek again. When he's talking in that second video, I don't know if he's did the link. If there's the guy, he's pretty happy there. He's got a little beard on, but whatever. Okay, so here is Derek. There's a force of gravity downwards. Yes, we all know that. But there's also the ground is supporting him and pushing him up. And this is what we call the normal force. Okay, and I'm going to go capital N for that. And just by the way, here, the word normal has a specific meaning. It actually means, the word normal means 90 degrees. It means the same thing as perpendicular. And so where's that 90 degrees from? Well, if the ground is this direction, then the normal force is going to be 90 degrees from the ground. Okay? So what happens if we put Derek or put some other object on a ground that's not horizontal? Okay, so this would be an example if I put, we call this an inclined plane. We would have gravity still downwards, but my normal force, it would go this direction. Okay, we're going to see that more later on. So the normal force doesn't always go up, and it's only there when there's an object that's resting on a surface. Okay, so if there's a ball falling, there's no normal force. Normal doesn't mean it's normally always there. Normal means it's 90 degrees to that surface. Okay, let's take a look at spring. Well, a spring, I usually say F of spring, or even shorter form, you can say Fs. And so where would we have an example of a force of a spring? I don't know, let's say if we had on a ceiling a spring and we tied an object to it, that object, just drawing a simple free body diagram of it, would have the force of gravity downwards on it, and would have a force of a spring pulling upwards on it. Okay, or another example for a spring might be, I don't know, let's say if we had a horizontal surface and then we compressed a spring up here and we put a cart here and we said, okay, let the spring go, what would happen here? We would have, well, the cart has a force of gravity downwards on it. It has a normal force up from that horizontal surface, and it also has a force of a spring on it. So clearly in this case it's unbalanced, In this case, it's balanced, at least if I draw those equal length. Friction. So there's two types of friction. We're going to do kinetic and then static. I usually don't differentiate too much between the two. Here's friction, FF, and it could come in two flavors. First, I'll say that kinetic means moving. So there's moving friction. This is the one that we often think of. Okay, so let's say that there is a book that's sliding along a surface. Let's consider all the forces acting on it. Well, we're going to have a force of gravity downwards. We're going to have a normal force to the right, and this is not a force arrow, that's just saying that's how it's moving, so I'm putting V for velocity. So the direction of kinetic friction is always opposes that motion. So if this object is sliding to the right, then there's going to be a force of friction to the left. Okay, so would you say balanced or unbalanced? That would be unbalanced, and it would be accelerating to the left. So that would look like moving to the right but slowing down. Okay, so again, force of friction, and that's the first version of it is kinetic if an object's moving. Well, the second one, where did I go? Is it below? Where's my force of friction static? I just need to go a little higher here. There it is, force of friction static. So again, I would just call this FF. I don't really differentiate it too often. Let's say that there's a really big heavy object there, and my job is to give it a push. I'm pushing on it really hard. I think I need a bigger head though. I think I need a bigger head so I can go. There's my head. And I'm unhappy because I am just not strong enough to move this thing. So I'm pushing, can you imagine? I'm pushing on this object, but I can't even get it started. Is it moving? No. Is it accelerating? No. So if I was to draw the free body diagram for it, it would be, well, there's a force of gravity downwards. There's a normal force upwards. There's the applied force, and we're coming to that. This is the force of Mr. Spicer pushing to the right. And I'm going to call that an applied force. And there's also a force of friction to the left. Okay, so it hasn't started moving yet. Now this is a little bit different. This static friction is only going to be enough. It's kind of like the normal force. The normal force supports this just so that it's equal with the force of gravity. Here, my force of friction is going to be just enough to stop it from moving. So let's say I pushed a little harder. You really can't tell from my diagram if I push harder, but if I was to push a little harder, the next diagram, what would happen is my applied force would be even greater, and then my friction force would be even greater, and I would still have the other two. If this friction wasn't enough, and if I pushed even harder, then maybe the friction, this is the point in which case it would start accelerating to the right. So the moral of the story here is the static friction is a little bit more complicated in that here's static, it's not moving, it's just enough to keep it not moving. Here it's still static friction because it's still keeping this thing not moving, but at this point now it's started to move, so now this is kinetic and it's sliding. Don't worry, I think I've given you more detail than you really need to worry about. The takeaway right now here is that friction is something that either opposes motion, or if it's static friction, that it's going to oppose the attempt at motion. Air resistance. How could I draw an example of air resistance? Let's say I've got a falling ball with a parachute here. There's my diagram of a parachute. Not really a great one. So this thing's falling down. First of all, air resistance is not always really a factor. It increases. It increases with size and shape. So in this case, if the parachute really kind of makes the thing look like a larger, kind of looks like a badminton birdie now. The parachute increases the size of the object, so to speak, and it also increases with speed. If you're like me, when you were a kid, as long as your parents didn't mind too much, and you're driving down the car, driving with your car in the summertime, and you stick your hand out. Oh boy, I'm going to try to draw a hand. So you stick your hand out the window, and the wind hits it. you could feel that air resistance, right? And the air resistance would depend upon how fast your car was driving and also the way that you held your hand, right? If you held your hand so it was kind of flat, right, then you didn't really notice it. But if you held your hand sideways, so I cannot draw at all, then you could change the shape of your hand or the size of your hand as it hit the wind and the speed. Usually we say F air for air resistance. It's really a type of friction. Tension force, it's about the only one that we don't use F. I just use capital T for tension. Here would be an example. Let's say that this is a ceiling and I tie a string to an object. So a tension, you need a string or a rope. And the free body diagram for this one would look like force of gravity downwards, tension force upwards. Okay, or let's say on a table you tied a string to a pulley and had something hanging. So you can imagine here the free body diagram for this object would look like there's a tension force left and then the force of gravity down and the normal force up. Okay, so you can have the string is pulling it in this case, and this example is just like that example over there. The last one, I mentioned it before, is the applied force, FA. And this is really when someone pushes, or someone or even something pushes or pulls. It's kind of a catch-all. So if a question says, Frank pushes the sled, you can say it's an applied force. If you said Frank pulls the sled with a rope, then you would probably put a tension force. Okay, so here's some basic rules about how to draw force diagrams, and I've already used the term a few times. A free body diagram and a force diagram means exactly the same thing. Sometimes I get kind of physics geeky and I say FBD instead of free body diagram, so that's just short. So here's how to draw FBDs. First of all, what is it? It's really just a simple vector diagram. Remember, vectors have directions and we use arrows for them. And we usually just draw an object as a box. So here's a textbook sitting on a desk. You could draw a version that kind of looks like it, or you could just draw it really, really simple and just have a box. And then you draw the arrows away from the box, okay? So even if I said I'm pushing the box from the left, that's not what the free body diagram would look like. You'd draw the arrow from the box going away from it. So a textbook sitting on a desk is going to have the force of gravity downwards and a normal force upwards. Each arrow represents a force. Label it. Here I have. The length of the arrow should give an approximate indication of the size, right? So if I had another larger textbook, I don't necessarily have to draw the box larger, but I would draw the force of gravity larger and the normal force larger. The other thing I like to do is if I know for sure that two forces are the same, I can put those little marks in them to indicate that they're equal lengths and equal sizes. Let's try example number 2. It says Mr. Spicer pushes the textbook to the right. Okay, so what would that look like? I'm pushing it to the right, so it would kind of look like that in real life, but in my free body diagram, this would be my force pushing to the right, so I start from the object and go away from it, and this is an applied force. Here's the force of gravity. Here's the normal force. Now the normal force is going to be canceling out the force of gravity because it's just enough to hold it up, not to accelerate it up, so it's not greater. So I know that those two forces are the same. I really don't know whether or not the applied force is larger, the same, or less than the force of gravity, so I'm just going to leave that. Here's a question that says a bucket of water attached by a rope is being pulled out of a well. Oh my goodness, this is going to be a challenge to my artistic ability here. So here is the bucket. It's got some water inside of there, and oh, it's inside of a well. Let's see. So it's inside of a well. There you go. And this whole thing is being pulled upwards. Okay. So what does it look like? Well, much easier to draw a free body diagram than an actual picture. The water has mass, the bucket has mass. We're going to consider this thing to have mass, so it has a force of gravity downwards. What's the upwards force? It's not resting on a surface. There's no normal force, but there is a tension because of that rope, so the upward one is tension. Now I really don't know, I know it's moving upwards, but I don't know which way it's accelerating. So I really don't know the relative lengths of those arrows. If it's accelerating upwards, then the tension force would be greater. If it's accelerating downwards, then the tension force would be less than the force of gravity. So here's what your worksheet looks like. We'll just do one question so you get a sense here. There is a block being pushed across the table. Consider only the forces acting upon the block. Okay, is there gravity present? Yes. Or absent? No. Gravity is present. Yes, it's there. Why? You know, I'm going to say typically don't worry about explanation unless you really feel like you need to talk about it. Is there a spring force? Well, there's no spring in this picture, so I'm going to say absent. Is there tension? Well, there's only tension if there's a rope or a string, so I'm going to say absent. Is there a normal force? In other words, is it resting on a surface? Yes, present. There's definitely a normal force. Is there friction? Well, it doesn't say anything here about to ignore friction, or if you see the word rough, then you for sure would put friction in here, so it's a bit of a judgment call. I would say in my real world experience, if I push a block across a table, there would be friction. So I'm going to say present. So I'm going to say normally there is friction. Nowhere in the question did it say ignore friction or frictionless. Is there air resistance? Well, really only air resistance is only a factor if you're moving quickly. And I don't think in this case, I'm going to say absent. And I'm going to say very low F air. So it's not enough to really be significant. And then I want you to actually draw a free body diagram somewhere. So let's put it over here. So we have to put gravity because I said it's present. So gravity is downwards. The next one is normal. There's a normal force upwards. And the normal force is actually going to be the same length as the force of gravity. Is there a... Well, the other one that's not mentioned here is the applied force, right? I think there's an applied force. I'm pushing it to the right. And it seems to me there's a friction force to the left. Okay. All right, that's it for now. And so you've got a few sheets to work on here, so you can do this in class. The pages 7 to 10 of the handout, and then when you're done that, you can do the MOP sub-level number 4. So we will see you in class.